Hi guys, welcome to the mathematics class for CBSE students of class 12. Today we will be learning about relations and functions. So this is going to be the first chapter. Okay. Now before we start, let's have a quick introduction about relations. So what is a relation? A relation is establishing a link or finding the relation between two objects or quantities. Okay. For example, you take an object A and another object B. If you are able to find the relation between these two given objects, then we can very well say that A is related to B. Okay. Now this in mathematics is denoted as small a, capital R, B, where A is an element, B is another element, and R is the relation. We can read this as A is related to B under the relation R. Okay. In other words, relation can also be defined as the set of ordered pairs of elements. What is relation? It is nothing but the set of ordered pairs of elements. Relation is always written only in pairs such as bracket A comma A, bracket A comma B, B comma A, and so on. Here A and B are two different elements, maybe from the same set or from different sets. Okay. Now there is an important note about relations. What is it? That is, the relation R will always be a subset of A cross A if in case the relation is from A to A. Okay. What they are trying to say is the relation R will always have elements from A cross A. It can't have elements outside A cross A. Okay. And then the relation R will always be a subset of A cross B if in case the relation is from A to B. Okay, again the same thing only. That is, the relation R will have elements only from A cross B. It can't be from outside A cross B. Okay. Now before we go any further, let's do a quick revision on what a Cartesian product is. You guys should have learned it earlier, but now anyway we will do a quick revision of it. Okay. What is a Cartesian product? Cartesian product of sets A and B is defined as the set of all ordered pairs of elements from sets A and B. That is, let's take for example set A equals 1, 2, 3 and set B equals 4, 5. Then A cross B will be what? A cross B will be, take the first element of set A and pair it with the first element of set B, that is 1, 4. Now the first element of set A has to be paired with the second element of set B, that is 1, 5. Now take the second element of set A, that is 2, and pair it with the first element of set B, you get 2, 4. Then 2, 5. Then take the third element of set A, that is 3. So you get 3, 4 and 3, 5. So these are the only possible pairs, okay, that we can get for A cross B. The order of these pairs is important as the first component of any pair should belong to set A and the second component of any pair to set B. So what they are saying is the first component of any pair, that for take this pair 1, 4 as an example. So the first component is 1. 1 should belong to set A. Now take the second component of the pair, that is 4. So 4 should belong to set B. Okay. Then so now let's find what is B cross A. What is B cross A? B cross A will be, now you start from B. So you take 4, 4, 1, 4, 2, 4, 3. Then 5, 5, 1, 5, 2 and 5, 3. So these are the values of B cross A. Now what do you see? Like from the above example, what do you find? We find that A cross B is not equal to B cross A. Why is it so? Because you take the first pair, that is 1, 4. Here the first pair is 4, 1. 1, 4 is always not equal to 4, 1. As we know, in relation, the order of the pair is very important. You reverse the order, then the element won't be the same. Okay. Now getting back to the concept of relations, let's take an example where A equals students of class 12 of a school. So you take set A to be the students of class 12 of some school, and you take set B to be the students of class 11 of some school. Okay. Then a relation from A to B can be such as what? R1 equals A comma B belonging to A cross B, where A is a brother of B. So they are defining a relation. This is an example of a relation from A to B, from set A to set B. Okay, where what they are saying is A comma B, it belongs to A cross B. Of course, it belongs to A cross B, and the relation is between A and B is A is brother of B. Okay, it is possible that in a school two brothers can be studying. Now it is possible, right? Like you can have a boy in class 12, which is A, and his brother can be studying in class 11, which is B. That is possible. Then R2 equals A comma B belonging to A cross B, where A is a sister of B. So this again is possible because A can be somebody in class 12 and the person's sister can be in class 11. That is B. Okay. Then R3 equals A comma B belonging to A cross B, where age of A is greater than the age of B. Of course, age of A with a student who belongs to class 12 is going to be greater than the age of B, someone who is belonging to class 11. There can be exceptions anyway, okay, because it doesn't always have to be greater. Then, moving on, let's go to types of relations. So there are so many types of relations. We will deal with them separately. Okay, we will go in depth into each type of relation. The first one is empty relation, then is universal relation, identity relation, reflexive relation, symmetric relation, transitive relation, and equivalence relation. Okay, now let's start with empty relation, also known as void relation. Okay, now as we know by now that a relation is a set that contains elements A comma B in ordered pairs. That is, only the pair of elements that satisfy the given condition for the relation. Okay, it is not always necessary for the elements of one or more sets to satisfy the given relation. For example, let's say set A B equals 3, 4, 5, 6, and the relation on it be defined as capital R is equal to A comma B, where A plus B equals 14, and A and B belongs to set capital A. So here they are taking an example like for set A, which is having elements such as 3, 4, 5, 6. Here they have defined a relation on A, okay, and the condition is A plus B should be equal to 14. Now, is this possible? Let's check it out. As we can see, the relation on set A is such that the sum of A and B should be equal to 14, which is not possible at all. Hence, there can be no values for the set R. Now, let's prove that. Okay, let's prove that R has no value. The first step would be to find the values of A cross A. First, we start by finding the values of A cross A. Okay, so A cross A will be equal to set A, that is 3, 4, 5, 6, again cross set A, 3, 4, 5, 6. So these are the possible pairs, all possible pairs of A cross A. 3, 3, 3, 4, 3, 5, 3, 6, 4, 3. So it goes on like that up till 6, 6. Here, even if you take the highest possible values of A and B, which is 6, 6. What is the highest possible value? The biggest pair is 6, 6. The relation would not be satisfied as their sum is not equal to 14. Even if you take the highest possible value, which is 6, 6, and you add both the elements, that is 6 plus 6 equals only 12. So, but the relation what it says, it should be equal to 14. So, even if you take the highest value, the relation won't be satisfied. This implies that no element A in set A is related to any element B in set A under the given relation, which is A plus B equals 14. Okay. So what is the empty relation? Let's define it. An empty or void relation is one where no element of the set is related to any other. Okay, that is set R equals a null set belonging to A cross A. Now, how can we say that a null set belongs to A cross A? We can say because a null set is always a subset of any given set. So a null set will always be a subset of A cross A. So R equals null set belonging to A cross A. Okay. Now moving on to the next relation, that is universal relation. Let us take the same set. Okay. A equals 3, 4, 5, 6 as an example. Suppose the relation is defined on set A and is capital R equals A, B, where A plus B should be greater than 1 and A and B belonging to set A. So here they are defining a relation, okay, in A such that the condition is A plus B should be greater than 1. Okay. Here we can easily note that any combination of ordered pairs from set A do satisfy the given relation. So whatever combination of ordered pairs you take, A plus B will always be will always be greater than 1. Okay, thus the set R will contain all elements of set A cross A. So for this set, if you find A cross A, you will get again the same value only. So all the pairs here, they are going to satisfy the relation which is A plus B is greater than 1. So what you can say from this, R equals A cross A. So the relation will always also be equal to A cross A. So now let's define what an universal relation is. A universal relation is one where every element of the set is related to each other. So A is related to B. Okay, again every element of the set is related to each other. In other words, the relation contains all elements of set A cross A. The relation contains all elements of the set A cross A. I hope you guys are catching up. Now let's move on to identity relation. So what is identity relation? It can be defined as one where every element of the set is related to itself only. Okay, that is, the elements in the relation will be of the order A, B, B, C, C. So here every element, that is A is related to only itself, only to A, B only to B, and C only to C, nothing else. It can't be A, B. It can't be A, C. Okay. For example, consider a set A equals 1, 2, 3, and the relation on A is R equals 1, 1, 2, 2, 3, 3. So they are given the values of R. Then we can say that this is an identity relation on A, as for every element in A there is an identical pair present in R. So any element you take from the relation A, you have its pair, you have its identical pair. So 2 you have 2, 2, 3 you have 3, 3. Okay. If in case, now let's take another example. If in case R, the values of R is equal to 1, 1, 2, 2, 3, 3 and 1, 2. Extra you have one more pair, that is 1, 2. Then can you say if this relation is an identity relation? No, because this relation is not identity, because the element 1, 2 doesn't satisfy the condition A, belonging to R. So this element, that is this pair, that is 1, 2, here A is 1. For identity relation, you need to have only the identical pair. This has to be 1. But since this is not 1, this is a different element. So this doesn't satisfy the condition A, belonging to R. So this relation, this example is not an identity relation. So next, another thing. If in case R equals 1, 1, 2, 2. What in this case? You have 1 and you have its pair 1, 1. You have 2 and you have its pair 2, 2. Is this relation identity? No. This is also not identity, because we have a pair missing, which is 3, 3. So all elements of set A should be present as identical pairs in the relation. Only then this relation can be called identity relation. Even if one pair is missing, okay, that relation can't be an identity relation. There's a point to note. In an identity relation, all elements of set A should be present in identical pairs. There can be nothing more or nothing less. Here, this is less. 3, 3 is missing. Here, this is more. 1, 2 is extra. So, if there is nothing more and nothing less, okay, then you can say that this is an identity relation. Now, let's move on to the next type of relation. That is, so the next type of relation is symmetric relation. What is a symmetric relation? Let's consider a relation R defined in a set A. Okay, if for every A1, A2, element A1, A2 belonging to R, A2, A1 also belongs to R. If for every A1, A2 belonging to R, A2, A1 also belongs to R, then the relation is said to be symmetric, where A1 and A2 belongs to set capital A. Okay, let's take an example. Set A is what? Elements 1, 2, 3. And the relation is what? 1, 2, 2, 3, 1, 3, 2, 1, 3, 2, and 3, 1. So this is an example. Okay. As we can see that in the above relation, for every pair of A1, A2, A2, A1 is also present. Here you see 1, 2, you have 2, 1. 2, 3, you have 3, 2. 1, 3, you have 3, 1. So for every pair which is in the form A1, A2, we have its symmetric form. That is A2, A1 is also present in the relation. So this relation is a symmetric relation. If in case the relation R1 is equal to 1, 2, 2, 3, 1, 3, 2, 1, 3, 2. So this is another example where you take the relation to be this. Is this relation a symmetric one? No, this relation is not symmetric. Why? As you can see, for 1, 2 you have 2, 1. Okay. For 2, 3 you have 3, 2. Okay. But for 1, 3 you don't have 3, 1. Okay. This relation is not symmetric. As for the pair 1, 3, its corresponding reverse order pair, that is 3, 1, is not present in the relation. So this relation is not symmetric. So you looked into an example where the relation was symmetric, and you also took an example where the relation is not symmetric. Okay. There is also a point to note. The symmetric relation needs to be checked only for those elements in the relation and not for all ordered pairs possible from set A. So what they are saying is like you need to check only within the relation, only for A1, A2, you have to check only for those elements within the relation. You don't have to go outside the relation and check. Okay. For instance, take set A equals 1, 2, 3 and the relation R2 equals 1, 2, 2, 1. So this is an example we are taking. Okay. Then this relation is said to be symmetric because for the ordered pair 1, 2, we have its reverse order 2, 1 in the relation. Okay. You get it, right? We never need to worry about any other possible ordered pairs that are outside the relation. Of course, set A cross A, you can have many possible ordered pairs. You may have 2, 1, you may have 3, 1, whatever. But we don't have to worry about that. We have to look only into the relation R, and if A1, A2 is in R, then A2, A1 also has to be in R if you are going to say that the relation is symmetric one. Okay. Now moving on to the next type of relation, that is transitive relation. A relation R in a set A can be said to be transitive if for every A1, A2 belonging to R and A2, A3 belonging to R, then if A1, A3 is also present in R, then that relation is called a transitive relation. Here the elements A1, A2 and A3, they all belong to set capital A. Now we will understand this with an example. Now consider set A equals 1, 2, 3, 4 and the relation R is equal to 1, 2, 2, 3 and 1, 3. Now is this relation a transitive one? Can you guess? Yes, this relation is transitive because for pairs 1, 2 and 2, 3, 1, 3 is also present in R. That is, this pair is of the form A1, A2 and this is of the form A2, A3. So for A1 and A1, A2 and A2, A3 belonging to R, we have A1, A3 belonging to R. So this proves that this relation is a transitive relation. Now take another example. If R1 equals 1 comma 2, 1 comma 3 and 1 comma 4. Is this relation transitive? A common answer would be no, because what you might do, you will just look at the relation, you don't have any pairs such as a1 comma a2, a2 comma a3. So you will right away say this is not a transitive relation, but most of us are wrong. The answer is yes. This relation is a transitive relation. How come? This is an exceptional case, okay? The reason behind that is, if in case there are no ordered pairs such as a comma b and b comma c in the given relation, then the relation is automatically assumed to be transitive. There is no need to do any further check. Here you take this relation, you don't have any ordered pairs such as a comma b and b comma c in this relation. Okay, you can't find any ordered pair in that form. So in that case, if you're not able to find any ordered pair such as a comma b and b comma c in a given relation, then you can say that the relation is transitive. You don't have to do any other further check. Okay, but there is a but also. Okay, but if there are ordered pairs such as a comma b and b comma c in the relation, but if you have ordered pairs such as a comma b and b comma c in the relation, then we need to check for a comma c to prove if the relation is transitive or not. Like if you have a comma b and b comma c in the relation, then we need to check for a comma c, which is 1 comma 3. Okay, in this example. Okay, so only after checking for a comma c, you will say if it is transitive or not. In which case, in case if you have ordered pairs such as a comma b and b comma c in the relation, but if there are no ordered pairs such as a comma b and b comma c in the relation, you will straight away say the relation is transitive. Okay, the next relation is equivalence relation. What is an equivalence relation? A relation R in a set A is said to be equivalent only if it is reflexive, symmetric and transitive. Okay, that is, the relation R has to satisfy all the three conditions of reflexivity, symmetric and transitivity if it needs to be called an equivalence relation. Okay, we will take an example. This example is actually from the textbook only. Example 1. Let T be the set of all triangles in a plane with R a relation in T given by R equals T1 comma T2 belonging to R, where T1 is congruent to T2. Check if R is an equivalence relation. Now, looking at the above question, what are we asked to check? We are asked to check if R is an equivalence relation. And what is the condition given? The condition given is T1 must be congruent to T2. Now, what is the meaning of congruent? If I am telling you T1 is congruent to T2, it means T1 and T2 have the same dimensions, as the same shape and size. If one object is congruent to another, it means both the objects have the same shape and size. Okay. Now that we are asked to check R is an equivalence relation, how do we start? We start with checking for reflexivity. Okay. For every T1 belonging to R, it implies that T1 comma T1 belongs to R, which in turn means that T1 is congruent to T1. Now, if I am telling you that T1 belongs to R, what does it mean? It satisfies the relation, that is T1 is congruent to T1. Okay. Now we know that any triangle is always congruent to itself. Of course, T1 will be congruent to T1 because they are the same triangles. The size and shape are going to be the same. Okay. Hence, we can say that T1 is congruent to T1 is true, which in turn implies that T1 comma T1 belongs to R. Get it? So this relation is reflexive. Okay. Now moving on. Let's check for symmetric. Okay. For every T1 comma T2 belonging to R, what does it imply? It implies that T1 is congruent to T2. Okay. It implies that T1 is congruent to T2. Now we know that if a triangle T1 is congruent to another triangle T2, then by default triangle T2 will also be congruent to triangle T1. If T1 is congruent to T2, it means T2 is also congruent to T1. This implies that, what does it imply? T2 comma T1 also belongs to the relation R. Now that both T1 comma T2 and T2 comma T1 belong to R, we can say that this relation is symmetric also. Okay, moving on, let's check for transitivity. For every T1, T2 belonging to R and T2, T3 belonging to R. Now let's say T1, T2 belongs to R and T2, T3 belongs to R. What does it imply? It implies that T1 is congruent to T2. Triangle 1 is congruent to triangle T2 and triangle 2 is congruent to triangle T3. You get it right? So T1 is congruent to T2 and T2 is congruent to T3. From these implications, we can arrive at a conclusion that T1 will be congruent to T3. Okay? Because T1 is congruent to T2 and T2 is congruent to T3, I can tell that T1 is also congruent to T3, which means T1, T3 belongs to the relation R. Hence, this relation is also proved to be transitive. What is the final conclusion now? The relation R is equivalence because it is reflexive, symmetric and transitive. Okay. Since it has proved all three relations, since reflexive is proved, symmetric is proved and transitive is proved, we can say relation R is an equivalence relation. So this finally brings us to the end of this video. Okay. In the upcoming video, that is the second part of this video, we will be looking into equivalence classes and exercise 1.1 problems. Thank you.